Oh, beautiful. Alrighty. Let's sort out this address walking. So I'm pretty sure this looks okay. That physical address that I've dumped looks like it's quite low. And I just want to see what that is in decimal. Let's do hex 7 F E 34. Let's divide that by 1024. Interesting. Yeah, so that's in the first couple of meg, or the first meg of physical. So that kind of checks out, I think, because the kernel memory map, I think, probably starts off pretty low in memory. So I'm going to take that as a good sign. Cool. So that checks out. I leave the login though. I'm guessing we're going to be walking a lot of page tables, so we wouldn't want logging in here. But for debugging purposes, it's perfectly fine right now. All right. All right, so that's the PML4. Let's have a look at this SDM and look for this nice white page. Always lights up my face. It's like a poor man's lighting solution for streamers. Stick a white page on your monitor. Alrighty, so we have just implemented this guy. I don't know why or if I yet need to care about the page level write through flags or the cache level. I know that I need to care about cache level when I'm dealing with mapping pages for register addresses. Like I have to disable caching when I'm using virtual memory pages over MMIO registers. But we can always circle back to that kind of stuff. For now, I just want to walk the tree, so you zoom out a bit here because it's a bit in my face. Physical address of the 4K byte aligned PML4 used for linear address translation. Okay, so we've done that. Now, so what kind of happens now is PML4 39 to 47. Oh, that is the index onto the PML4. So what that equates to is once I've located the PML4, which is this here, and we want to get to the entry into the PML4, we utilize the virtual address, which the documentation is calling the linear address. And in this macro here, so we're bit shifting 39 to the right, and we're picking 9 bits. So we look at the manual here, we can see 39 to 47, the PML4. If I just put this next to these macros, so the directory pointer is at 30 to 38, which is this PDPTE index macro, and then we've got 21 to 29, so that checks out. And then we've got the final level 4 table at 12, and then the offset from 0 to 11. So I think FFF is 11 bytes, right? Let's have a look. X FFF. Oh, it's 12 bytes. Is it 12? Oh, it is. It's 12 bytes including 0. Keep forgetting it's 0 based. So 0xFFF is perfect. All good. Okay. I don't know if anybody else uses the programmer view in the Windows calculator as much as I do. A lifesaver while I'm still getting used to thinking of hexadecimal to binary and some of these really common bit layouts. Okay, what is next? So our entries are okay. Picking that from the virtual address. The offset, that was fine. So I think what else was incorrect was I need to verify this mask bit 1. Because I need to, I've seen this in the books that I've read, but there are definitely some discrepancies in the books I've read into what I'm reading in the SDM. So, somebody mentioned that I need to take note of checking if the page is 4K 2 meg or a gig. But that's for 5-level paging. And we're not using 5-level paging, we're using 4-level. So figure 8 illustrates 4-level paging when it produces a 4 KB page. Oh wait, it's saying that we can produce a 2 meg page. Is this possible then? How would you know? Where are the flags? The offset is a lot bigger in that linear address. So this is a different format on the linear address. How would you know which one you're dealing with? Not all processors support 1 GB pages. Does it tell us for level paging protection key? Access rights of each linear address. The remainder of the section describes the translation process used by 4-level in more detail, as well as how the page size and protection key are determined. Okay, good. That's what I'm after. Because the process used by the 2 paging modes is similar, they're described together with any differences identified in the following items. So with 5-level paging, a 4 KB naturally aligned PML5 table is located at the physical address specified in bits 5112 of CR3. I did not want to click that. I've just skipped back and I don't know how to go back in this viewer. That sucks. Don't click things. I need to blink more. My eyes are stinging. Okay, so for level paging does not use a PML5 table and omits the step. Okay, PML5 table comprises of 5 12 64-byte entries. All right, let's just ignore that. So a 4 kilobyte naturally aligned PML4 table is located at the physical address specified in bits 51 to 12 of CR3. Or in bits 5512 of the PML5 for 5 level, which is whatever. The PML4 table comprises of 512 64-bit entries, which are the PML4Es, and the PML4E is selected using the physical address defined as follows. So bits 51 to 12 CR3, bits 11 to 3 to 11, bits 3 to 11 are bits 39 to 47 of the linear address. What does that mean? Because the PML4E is identified using bits 39 to 47, it's control access to a 512 gigabyte region of the linear address space. Bits 12 to 51 are from the PML4E. Oh, it's telling me that to extract the location from the entry. Is that correct though? It's a little confusing. I'm not sure what the correlation is between these two statements. Bits 3 to 11 are bits 39 and 47 of the linear address. Is it just telling me that the value from the source linear address is the same as 3 to 11 in the PML4 table entry? Is that what it's saying? I think so. "12 to 51, isn't that the same as this mask up here?" Let's just call that address mask, because I've got a feeling I'm going to need to reuse that mask for these other addresses. So this, I think this is where this is just nonsense. So me converting this PML4E. So I might have to macro this, to be honest. I guess I could. Because this just becomes I move this over by 12 byte shifts, and then I mask it with the address mask. Document. So 51 to 12, right? So you get 12 over, and you got 40 bits in the mask, which is pulling that new. Hmm. It's 12 to 51 off from the PML4 entry. Using the PDPTE entry depends on the PS flag bit 7. Oh, here it is. It maps a 1 GB page. Oh, I see what it means now. So once you walk to the second level, you can stop there and say that you map to a 1 gig page. So bit 7, what does PS mean though? I want to make a meaningful name for this. Let's just make some notes here. All right, so when we arrive at the PDPTE, we're going to check for bit 7. If that the PDPT entry maps a 1 GB page. And at this point, we can resolve the address. The address's protection key is the value of bits 59 to 62. So we can resolve this from bits 30, so 51 to 30. I think is what it means. I'm just going to put this in kind of brackets because I don't know what we need to know about the protection key is. It's 62 and 59. And then I'm guessing that if we don't resolve to a 1 GB page here, we carry on going to the next entry, and if it flags as a PS flag there, let's just call this PS because that's what the doc called it. PS flag of a PDPTE is reserved and must be 0. If the flag, if the P flag is 1, oh, it must be 0 if 1 gigabyte pages are not supported. So you can query CPU ID for here it is. 1 gigabyte pages may be supported with 4-level paging and 5-level paging. Another shopping list task. So it's 016, 1H. It's in EDX NX, which is bit 20 equals 1. Sorry, bit 26. And it calls this page 1 GB. 1 GB pages may be supported. What about what was the other one? Is there a different routine for determining why are you getting ads? Why are you getting ads? It is because, oh shit, it's because I'm an affiliate. But I have to turn that off in the stream account. Let me see if I can turn that off. Hold on. Create a dashboard, maybe. Monetization, ads. Here we go. Ads manager. How many minutes of ads do you want to run per hour? 3 minutes of ads per hour? I want to turn them off. How do I turn them off? Ads not scheduled. Dude, I don't want the ad money. I only stream for fun. I think that's done it. %30 net ad revenue share. A pack of Monster Munch, sure. Yeah, we'll see if that works. Just let me know if you get smacked with ads again. Alrighty. So 1 gigabyte page support, and I've lost my where I was. I need to remember the page number that I was reading because it fucks me up when I click links. Paging. Here it is, linear address translation. So the next one was a 2 megabyte region. Oh no, this is not what I should be reading. Wait. I've lost my way now. I think it's way past this. Full level paging 4.5, 4.52. I think it's this here. Yep, we're back. What page am I on? 424. Well, page 124. What did you have to eat? You had curry? Oh, that sounds good. I had a pie with gravy. That's all I ate for dinner tonight. Yeah, I have no hardly any food in. I was really tempted to get an Indian takeaway, but I don't like doing that in the week, like randomly. So I settled with the lonely pie that I found in my freezer. But I certainly wouldn't have hesitated if it was like Friday or the weekend, you know? You get hangry. Never felt hangry. I know some people that I work with say that, but I can't imagine like being emotionally angry because I'm hungry. Like when I'm hungry, I'm actually just like excited to eat. Like it's the opposite for me. I'm not angry. I'm like, oh, I'm so looking forward to eating, you know? Like I get excited thinking about food. Food. I've been training heavy this week, so I'm extra hungry this week. Low energy levels can affect mood on a biology level, so people can't cope well with low sugar. Oh, I have to admit though, I can feel more emotional when I'm low energy. It's being moderated because the term NERGRY, why is that a banned term? But I've clicked something in it. Like Twitch is so different to when it was like 6 months ago when I was streaming. Like there's so much more moderation and shit going on. But it's now added the word to the allowed list, and you can say it how much you want now. Yeah, don't worry about spelling or whatever. I'm not a spelling Nazi. Um, yeah, exactly. You've got like the smarts in like 4 languages, right? And here's me on just a single language. Who am I to make fun of someone for not speaking perfectly, you know? A dirty foreigner. Hello there. Nice to see you again, buddy. Oh, hi, Walker. Is that Walker from Twitter? Yeah, GB, I was hoping you were going to turn up. Um, kind of left you guys hanging for 6 months because summer kicked in and I decided to become a weekend hiker. And now that summer's gone, we're back, you know. You invited him? Oh, that's cool. Walker's cool. Yeah, Walker, summer literally just like switched off in a day, and I'm not even kidding. Like the 1st of September hit, and everyone was like, summer has now disappeared. And I was driving to work, and all I could see was leaves falling off the trees, like someone hit a light switch. And I was like, okay, it's now autumn. Yeah, I touched grass this summer, man. Like, I got this idea at the start of summer. I was like, oh my God, I can't stand the thought of spending the entire summer coding my OS. And I've got like the whole of the Peak District right on my doorstep. So, yeah, I've been exploring the Peak District every weekend now. And I'm probably still going to do it for a few more weekends while the weather's still warm. Yeah, Walker, you're in the US now, aren't you? But I remember you came back here a while ago. Like you went to Scotland because I enjoyed that tweet you had about meeting. You bumped into somebody that you went to school with and they recognized you, and I was like, holy shit. Like if I saw somebody that I went to school with, I'd be like, who the fuck are you? Yeah, you're in Texas, dude. That's so cool. What a weather difference, right? But your projects that you've been up to Walker, they're really fun. Like all these like that Space Invaders you were doing, you know? They're just like fun little projects. I was like, oh man, that's cool. Like it's fun doing silly like simple stuff like that every now and again. Yeah, Texas summers, man. It's probably like the worst in the world. Um, and that dry heat too. Yeah, my roots are in game dev, dude. So when I see like people making games and stuff, I'm like, oh man, that's so cool. Like that's where all my dev began. So it's like the core memories that I have are on the Commodore 64, writing games and whatever. Oh, you get humidity. I thought you had like a dry heat period in Texas, and it can get pretty bad. You're still getting plus 30-degree weather, Victoria? Like, we didn't even get above 25 here in the Midlands. Like, it's 22 in my room right now, and it's kind of humid. 32 would be gross, man. I'd have to invest in air conditioning. Every year in the Midlands, I say to myself, I'm going to get air conditioning. I could get like an air conditioner installed into this like one room that I'm always in this room, right? My computer room. So I could spend like £800 on getting some dude to come drill a hole and install an AC fan. And my friend has done it, and he's like, "Oh God, it's perfect. It's heaven." He's like, "Martin, you need to do this. You will wish you would have done it sooner." You have AC until November, dude. I'm in hoodie. Like this hoodie on the back of my chair is what I wore to work today, and I've only taken it off because it's quite warm in my house. But yeah, it's like hoodie weather in the Midlands now. But it's quite moist, man. I hate humidity. Like I don't mind heat, but when it's too humid, it's like when I work out, I can't do much without sweating my ass off, and it's uncomfortable. 30 degrees here, and this is the last heat wave of the year. Where are you, GB? You're British, aren't you? If I remember. Oh, you're in the US, sorry. Was humid here the other week at the mist set, and I felt like I could swim. Oh yeah, there was some mornings where I went out because I'm growing vegetables. All my tomatoes had like condensation on them, and I'm like, what the hell? It's summer, dude. But yeah, it's still quite humid even now, and it's horrible. It's kind of cooler too the more north you go in the UK, I think. Like Scotland have it nice and comfortable. 42%. That's not bad. It's 88% here right now. And you can definitely feel that. A northerner? Do you think the Midlands is the northerners, Victoria? Is that your perception? I am definitely not a northerner. You can just tell by my accent, though. I think in the Midlands it's so neutral. That's so funny. Because the true north is everything above that blue line. The south is quite accurate, obviously. Cornwall and yeah, seriously, Walker, it's like it's 88 right now, dude. I don't know where it's coming from. Oh my god. Victoria's in 100% almost. That's well, you can't ever have 100% because you'd suffocate. It's a nice, interesting fact for you guys. If you're in 100% humidity, your lungs will fill with water and you will suffocate to death. Don't ask me how I know this. I remember reading there's a certain cave in the world somewhere that has a stupidly high humidity that can literally suffocate you if you go inside of it just by breathing. I think that's where I found out about that. You're a fish? How interesting. All right, now that we've established how comfortable we all are in our locations of the world, I am currently, just to catch you up to as well, GB. So where we left off 6 months ago, man. Now it's time for feed. Yes. How many people are watching right now? It's like feed at 5 viewers. Oh, we have 5 viewers. Okay, right. Time for feed. Let's go. Yeah, so 6 months ago, this OS project was freaking flashing out, doing a hard drive driver, and we got cock blocked by needing to map the registers into virtual memory, which, by the way, I've now suddenly realized that we do not need to. So if I really wanted to, I could come back to this and complete the hard drive driver. But I'd be kind of like cheating myself, because at some point we are absolutely going to need a virtual memory manager. If we don't have a virtual memory manager, we will not be able to do processes and threads and stuff like that, because we need applications need a virtual memory space, right? They're not all going to just share the same memory map. So the kernel gets its own memory space. Every program or process, if you like, gets its own memory space, as you know, in Windows programming or whatever, OS coding, that your virtual memory begins at 0 in every application. But yeah, this is what the whole CPU has this concept of setting a pointer in one of the registers on the CPU, and it's like, okay, that pointer is the beginning of your tree, and then the page tables inside of that tree are what point you ultimately to a physical piece of RAM somewhere in the system. So applications can all start at 0, but all applications have a base pointer in this register of where their memory map is. So your 0 is always relative to your CR3 pointer, where your memory map begins. And I know that probably sounds hella confusing if you've not done it before. Yeah, I've seen people. There's some crazy ass people in the OS Dev Discord who are writing their own OSs in different languages. So we've got a guy writing his OS in Rust. We've got a guy writing his OS in C++, and there's somebody, and he's absolutely batshit crazy. He's writing his OS in pure assembly. And the thing is, he's doing a good job, but it's amazing. Go wouldn't work because of its compilation. So you need something that can produce like an ELF image, like a raw CPU program. Go is like, you know, here's a memory manager, here's a scheduler, like your Go routine library, you know, and then your garbage collector, your memory sweep and cleanup and all that stuff is all packed inside of that exe. It would be awesome to use Go, obviously, no memory management. Yeah, it's just one of the very first things you learn, like day one, Walker. Like it tells you like you need a really raw way of compiling stuff. So you need a special build of GCC. You need to probably work, like it's easier to dev on Linux because there's less red tape. I mean, you can compile stuff on Windows if you get hold of like the compilers that can produce the raw images. But even like a standard GCC build, like doing a C++ build or even a C build without the specific compiler that you need, it packs a load of libraries into that exe, which you don't want, like the standard library of C. And when we compile, we don't have any of the standard C library, right? The kernel does not have string functions. It doesn't have file IO. It doesn't have, yeah, exactly. It doesn't have stdio or standard lib. So like if I show you in here, so you've got an str C file, which is my own re-implementation of things like VSN printf, right? So I had to write all of this to re-implement, you know, the format specifiers. Yeah, I2S. I've got the whole L2A, but it's all in here. Like, you know, just had to write it all over again. And that's probably one of the, a lot of people say that's quite painful when doing your own OS, but I find it quite refreshing. So like, all the string functions are just like, you know, that's just a fun library to write, but like your date time stuff, your localization stuff, especially your file IO, like that's really closely knit to exactly how you want to implement a file system in your OS, which is again completely up to you. A lot of people use like a virtual file system. So like Linux is the best example of that, how everything lives in /dev, or it is a path, should I say, like devices are in the virtual file system. So like things in /dev are devices that have registered in the file system. So you can grab, there's papers on this in the OS dev community where you can like read some guy's, you know, whole book on how to implement a VFS. And you just take that abstract and you can put it in your own OS and you can be like, okay, well, I'm going to make it like Linux, right? And I'm going to have all my devices register in the VFS. And then I can interact with them and read and write to the device memory through the VFS, as well as writing to disk locations and RAM locations and whatever. It's all virtualized. You're making BIOS calls in assembly then for low-level stuff. It's a little different to making BIOS calls. So BIOS calls are used in the bootloader, which is the bit of code that bootstraps your kernel, right? So before your OS loads, your BIOS initializes a program and it's like, okay, you can run BIOS functions in there. But the second you come out of that area and you're in kernel land, you've lost all of the BIOS functionality, right? You can't, there's no interrupts, there's no, you know, fun file IO that you, or keyboard stuff that you can call in the BIOS anymore. And where that leaves you is if I look at the keyboard driver. So you have to write a keyboard driver to get access to the keyboard. And you can see here I've had to implement all the scan codes. So you guys probably know this from freaking any Java or .NET stuff you've written, right? So you've got a keyboard map, scan codes that come from the device, and you've got to map those to actual characters that are on screen. And the way you talk to the hardware are through ports. So if I show you, there's these assembly commands. So if I just go into here, so there's an instruction called like inb, which is read a byte, write a byte. Sorry, that's right. Input W is receive a word 16-bit value, and then is in L, which receives a 32-bit value. But you have special locations in memory that are input-output locations. So what happens is all the devices in your machine, like keyboards, your graphics card, the chips on the motherboard themselves, they all go and reserve an area in RAM to say, I'm going to claim this, you know, physical part of your RAM, and I'm going to use that as my gateway to give you information from this device, right? So you find there are some standard locations that you then map to. You're like, okay, the keyboard's here, so I'll read and write from those locations, right? So this PS2 driver here is fixed on these addresses. And you're just sending commands and reading data from those memory IO locations. And then things like the frame buffer, which is, I think I saw you with some code recently on accessing the frame buffer. So part of your video RAM is mapped in RAM. And as you write into that frame buffer area, you'll write the pixels on the screen. Yeah, so if you think about a BIOS call that would do a file operation on a disk, right? So you've got some code that lives in the BIOS chip that knows how to read FAT32 from a standard drive, right? It's just some code that someone's implemented for convenience, right? But now that you're out of the BIOS, you're not in that land anymore. Well, how do you get to a FAT32 drive? Well, you've got to navigate the PCI bus, right? So you need to write some code that understands how to navigate PCI. And then once you've navigated the PCI bus and you've found out what's connected on the bus, for example, oh, I found a hard drive connected on a serial ATA connection, or there's an NVMe drive connected on the PCI bus. So now that you've recognized as an NVMe drive, you now need to find out where its registers are mapped in RAM to talk to it. And now you need to write a protocol to initialize and talk with the NVMe drive, right? And then now that you can get access to the drive, well, how do you get access to the files and folders? Well, what protocol are we using? Is it ext? Is it FAT32? Is it NTFS? So now you've got to write the protocol of the actual data that lives in the drive. And at that point, you're reading like sectors and, pages in sectors and things like that. And then it's up to you how you interpret, like, where's the FAT table, where's the directory locations, where's the file locations, and that kind of stuff. Which I find fun, actually. I was looking forward to doing all of this. So I was kind of like beelining to implementing the NVMe controller. And if I show you, let's see. Yeah, so this is the kernel log when it boots up. And on this display, it says, for example, the PCI reports in the middle there. It's like, okay, I found a bridge, I found a display controller, found a network controller. There's a mass storage controller, which is potentially where all your drives are connected to. And then there's a serial ATA controller, an SM bus. And then it goes ahead and initializes the NVMe, which again just initializes. I'm not talking to that thing yet. Yeah, PCI to a disk to then actual format of data. Yeah, QEMU is the x86 emulator that you typically write OSs against. So what's really fun with this is it's super easy. So for example, if I close that window by just killing the kernel, do make run, all that make run has done is fired up. I've lost the log now, but it just runs QEMU with your disk image. So you compile the kernel into a disk image, and then you tell QEMU, load this disk, and then it behaves like a normal x86 PC, where it initializes a BIOS, it runs your bootloader, it loads your kernel into memory, and then invokes the kernel. Too low level? Yeah, it's definitely just something out of enjoyment, really. The guys that I work with will love asking me about demystifying what an OS looks like. Like, how do you even start writing one? How does it load? How do you start writing C? All those questions that people are like, how do you even begin doing this? And it's just the thing, like, you start in a kernel main function, like here, look, is like void main. That's it. That's where you begin. And then you start dipping into writing assembly. And reading the manuals that Intel provide us to tell us where things are in memory. time I actually feel dumb. It's not your type of programming, but the question on where to start is the same question you can get for any complex application. When I wrote Wi-Fi Vault, people ask me all the time, where do you start? Yeah. And there's always like a simple one point where everything begins, right? And it's the same here. It's like everything begins here in this one function. And then the bit in the middle is just you writing an OS. If that makes sense. It's like it's like one of the first. Here's a good example of like day one hello world kernel development, right? Is you need a log. Like you're not going to be able to tell why your kernel crashed if you can't even understand text, right? You can't see a log. So what you do is you pipe text down the COM1 port. So the emulator says, okay, you've got a COM port. We can connect a file so that when we receive data on the COM port, we'll just write it to a file. So then for my kernel, I'm like, okay, as long as I'm shoving data down the COM port, I'm going to capture it in a file. So all these files here are my logs before I had the UI. So this here is the entire log of the kernel beginning. So at the top here, I'm just like, the very first thing that I wanted to do was get the graphics going so I could write things to the screen. And then I'm doing things like interrogating the CPU setup, you know, how many cores, processors, frequency, speed. But yeah, most people will have, even if you're not using the emulator, some people will use like an old 386 or a 486 PC, and they'll get one with a COM port, and they'll plug something into the COM port to capture that data, and write it somewhere that you can see. And that's the only way you've got to peek into what the kernel's doing. So like day one is like, okay, I'm going to write data to a COM port. And it's like, right, okay, well, how do I do that? So, you know, in here, if I show you like one of the very first, what is it, serial.c. So not a lot of code in here. So you read on the OS dev community, it's like, right, so what are the ports for writing to the COM port? And they give you the port addresses. So you know now, okay, I need this out function. So you need to write that out function. What does that do? Well, that's a bit of assembly. That calls the outb instruction. That just tells the CPU to send some data to a port, right? So that's hello world, right? One line of assembly, get some port addresses, and then push some data down the port, and that's it, right? Job done. You've got data flowing down the COM port. You've now got a log. Now I've got a log. I can read and write interesting shit now, right? As you begin then to write more assembly and poking around on the chips and all this stuff like memory and RAM, and you want to see where things are and how big things are. You want to start logging it and see what you're working with. And then it just grows out from there, really. Breakpoints do work. They do. You can hook into the emulator process with, let me see, I've made some notes on this in my docs folder, debugging. So I think I can do it in here, make debug. Is that working? NumQ's deprecated. Oh, I know what's happened. It started the emulator in paused mode, waiting for you to hook a terminal on. So what you can do now is you can run GDB or OS, and then once you're in GDB, target remote 1234, that connects to the debugger. Now you're in memory. And now if I want to add a breakpoint, I can do break kernel main. Breakpoint pending on future shared library load, sure. It's just saying that it hasn't loaded code to understand what kernel main is yet, but it'll remember that I want to break there. And then if I hit C, that tells the emulator to run. And now the emulator is running, the breakpoint was set. It didn't hit it for some reason. But now that I'm in the GDB debugger here, there's all sorts of like commands that I can't remember. You can inspect memory, set breakpoints on lines, function names. You can like mem dump if you want to inspect memory. But yeah, it's a bit awkward. I don't remember the GDB commands. So my debugging, sometimes I have to go into the debugger though when I've got memory issues, like some really what the fuck problems, where I'm looking at the assembly and I'm like, why are you doing that? I didn't ask you to do that. Why is it running this instruction? So I mainly go off the logs because it's so fast to just boot the kernel up. So like make build, 2 seconds, make run. Bam, the emulator's up and running. Hit enter, done, right? Got a log. So as I'm like writing this virtual memory manager, and I put log lines in here, I just keep running the kernel over and over. Yeah, there's probably a UI version of that GDB. Like that's just the command level or the CLI version of it. Debugging. I think one of the hardest things, so one of the most difficult things in debugging in OS Dev is I've wrote a load of code here and it does a lot of stuff and it appears to come out with an answer, which happens to be a physical address. So the purpose of this function here is it's like, give me a virtual address, which means like a process level. Think of a program saying that I've got a variable at 04 address, right? It's not really 04. It's the program's 04. And I need to translate that program's 04 to where that actual memory is in RAM physically. So this walk function says, given a virtual address, I will return back to you the physical RAM address of where that memory really is. But all this code kind of runs, and I'm like, I've no idea of verifying if this physical address yet resolves correctly until I start trying to use it for something. But I'm going to spend a lot of time in here because it's not just walking down the page tables. It's like, okay, if a process asks for some memory, as in declare a variable on the stack or declare a variable on the heap, that's going to be a call to the kernel to say, hey, I need you to allocate me some memory in my program, right? So this virtual memory manager has got to say, oh, there's a program here that's asked for a bit of memory. Let's go register them in the paging map. So I need to come into the page tables. I need to find them a place to live, allocate them some memory in the physical memory manager. So I've got a physical memory manager too called, is this file over here, and all this deals with is physical memory. So the virtual manager goes, I will virtually allocate you some memory, and I'll go ask the physical memory manager to physically go and reserve some memory in RAM. So this is like, this virtual manager is the layer on top of physical memory. and it's all CPU level stuff. So this is not something that you're like, it's not a concept that you're making up in code. The CPU itself has paging built into it. So the reason I keep looking into the Intel manual here is because paging is actually built into the CPU. And it puts a load of protection around it and stops like people writing really malicious code. And for example, there's so much protection now built into the CPU where it becomes difficult to look into another program's memory locations or access the kernel, like just bypassing all security and just going straight to kernel calls and doing all sorts of shit with the kernel. The CPU itself protects everything in the OS from doing that. So you're talking to the CPU to say, I want these memory locations, they're going to be protected, they're going to be user level, they're going to be kernel level, and the CPU then makes sure that future calls into those memory locations are permission checked, right? And there's lots of like, it does some nice, it's got some nice features for you too, like it does caching of like page swapping and that kind of thing to optimize the memory reads and writes. So unfortunately, for me, really, this is why I'm taking it super, super slow, trying to understand how this paging manager works at the Intel manual level to fully understand how the x86 processor operates so that I can work with it, you know? Like once I've got paging under control and I'm fully understanding of what it does and how to control it, I can then progress to writing the concept of having threads with separate stacks and separate memory maps and processes that all have their own virtual memory maps now because I know how to operate the x86 virtual memory manager. Sorry if I've waffled on. It's just everything is like a rabbit hole of a rabbit hole, but it's got a limit. And my brain loves the complication. Like, I like having these challenges. There are some people who write OSs where, so when I was just touching on how you have like user space permission and you have ring 0 level, which is kernel. You might have heard it called ring 0. But some people write operating systems entirely in like full privilege mode. So if you're running a process, that guy's got full access to everything the kernel can do. And it can dip into programs all around itself. You know, it can do whatever it wants. Complete Wild West. The CPU is your oyster, right? And it's for speed really, because having the processor do things like permission checking and switching between privilege levels, well, it comes at a cost, you know. And people are like, well, if I remove all the privilege checking and all the permission checking, I've actually got faster programs because there's no context switches. Like it's crazy to me. Like when you think about writing this kernel and how often you have to switch the stack between threads and the memory locations, like the virtual memory pages, are constantly being swapped in and out. But every time you give a slice of the CPU to a program, so blazingly fast, it's insane. Like you actually can see how insane it is when you're in the kernel. Like the amount of context switches it does per second. And it's just flying through the instructions like crazy. And there's so many manuals too. So like this is the official Intel website for reading up on the architecture of CPUs, like a 64-bit processor, and they've got like manual after manual for different features of the CPU, right? Like power management is an entire document for itself. Like how do you put the computer into hibernation mode? How do you detect when you want to restore from hibernate? How do you make it so that a hard disk, when it activates, it turns the computer on? Or how do you have a USB wake-up device? It's all power management stuff. And there's a whole guide to doing that kind of thing in an operating system if you want to do it. But this main guide that I'm looking at is just all about the basic functionality of the CPU. So if I go to the contents, you'll just see the high level of how complex a CPU is. Right? So you've got each kind of like subheading under here is like a feature in the CPU. So like these global and local descriptor tables, gates, task segments, interrupt and exception handling, memory management, registers, protected mode, paging, interrupt and exception handling, user interrupts, task management, multiprocessor. So when you start waking up the cores, and that's another big part of OS dev, is that you're the chef, right? You're the scheduler. So the computer turns around to you and says, here's 16 cores, but they're all asleep. You let me know when you want to wake them up, and you've got work for them to do. And then it's up to your code, how you write. Okay, how are you going to dish the work out to those 15 cores? Like, just give them all an even slice of time. Prioritize kernel demands. Prioritize I/O demands, you know? Someone just replied to me in disk. For your case, 3912 will give you a page number. If you want an address, you need those 12 bottom bits present and zeroed. I wish I could understand what he means. I think he's telling me how to get the physical address. The bottom 12. When the Intel P&E cores came out, there was a new processor scheduler built into Windows 11 called the Thread Director. Yeah, there's I think there's a section in the document that talks about like hyper-threading technology. It might come under that. Memory cache control, power and thermal management, machine checking. It might be in a different document. I'm actually quite surprised how there's a lot of virtual machine code built into the CPU as well. Like virtualization, the CPU is well aware of integrating with virtual machine environments at the CPU level. So there's like extensions you can call into to optimize it running in a VM. Like the way it manages memory and stuff like that. There's a whole section here on it. I'm trying to find. Pretty sure there was hyperthreading in here. It's definitely probably in a different document. I've definitely seen it as like a massive heading. But yeah, if you look in, well, it's not like every day someone looks into the Linux source code, but when you begin writing your own OS, you'll have a bit more confidence into looking into like the Linux kernel, because you can find things in its source code that you know it has to have. Like, for example, when you're writing the keyboard driver, right? Well, Linux must have that same port number. So you can do a scan in the Linux kernel looking for that port number, and then you'll find the file where they're initializing the keyboard driver. And you're like, okay, how did they in Linux write the keyboard driver? And you're free to look at how they did it and copy them, right? Like they create a queue of keys, and it's like, okay, what's the key size? It's 500 characters, and what does it do when it blows up? Oh, it just blanks the queue and carries on. So, and that's Linux's solution. And you don't have to do it like the way Linux does it. But it's cool that you can go into the Linux OS. Sorry, to relate back to your point about processors, it's an absolute treasure trove of seeing the amount of CPUs that are in the wild. And it's kind of mind-blowing. Like, it's got every CPU you've ever heard of, and then times that by 50. From like 1970 something. It's got like Palm OS code in there, and it's just got custom CPU code for every CPU you've ever seen, and abstracted in the C language in such a nice way that the OS kernel interacts with the CPU at a really virtualized level. Like paging, yes, on the x86 64-bit processor from Intel, yes, paging, done in this way using a radix tree. Not necessarily the way paging works on a different CPU, but again, abstracted away from you. Temple OS, I think, is a 32-bit operating system, right? Is it 64-bit? Oh no, it's 64-bit. Yeah, that's pretty good. The reason I have to ask if it's 32 or 64 is a lot changes between 32 and 64-bit, and it's not even worth bothering with 32-bit knowledge with how different it is to 64. Marion, yeah, my head is stuck in the Intel SDMs at the moment as we're figuring out the paging stuff. Cheap viewers? Are they calling? You hear that, guys? Are you the expensive ones? Kind of sucks, as I don't even know how to moderate that line. Like, where are my mod tools? I remember being able to click on the user and like ban his ass. Mod actions. Ban. There we go. It's just hidden away. Sorry, I sound like such a boomer. Like, oh my god, where's the button? Give me mod. You want mod, Victoria? Oh my god, do I have Streamlabs notifications? Did you guys see a Streamlab pop up? Whoever just followed, thank you. I should go to my dashboard so I can see my notifications. Ah, I can see them now. Yeah, thanks for the follows. homies. I don't mind modding you. Yeah, welcome in. Sorry, Marion. I hope that's how you pronounce your name. I'm terrible with names. I'm sorry. It's how my brain works. I'm awful with names. Welcome in to a crazy project of us writing our own operating system. And I can certainly show you code, and I can show you the operating system running if you like. You reloaded the page and got ads again? Well, thank you very much for your kind donation, Victoria. I can now buy a Twix. That's funny, I had a Twix in work today. Yeah, so we're writing an OS, Marion, and it's a cool project, and because I feel like for my career, it's like the end game. Like, how many different ways do I want to think about writing software in my life? You know, like I've been a web developer for X years. I've been a desktop developer for X years. I've done mobile apps. I've done games, 3D and 2D. And I'm like, what else? You know, what is left? And I'm like, I know, let's do low-level embedded stuff. Or what could I do? Oh, let's write an OS. Let's go crazy and just sign up to writing an OS, you know? And here we are. Oh, you've been online for 20 years? Oh, cool. So you're well versed in internet culture. But yeah, and what's funny that I've noticed about people who do OS dev is, well, with anything, right? Like if someone tells you they're a web dev and they work with React, you have an opinion. If someone tells you they're a Visual Basic.NET developer and they write WinForms, you have an opinion. Right? You're like judging that person, like you write in VB.NET and you do WinForms, you noob. You know, it just has a connotation. Like Java developers, .NET developers, Go developers, Rust developers. And unfortunately, the second you tell someone like, oh yeah, I'm writing my own language or I'm writing an OS, people are like, oh, you must be a cracked dev, right? And you're like, no, I am not anything clever. I'm reading a manual that is explaining to me concepts and details, and I'm translating that into code, just like you would have done in any other domain in your life. What the hell is cracked? Cracked is the new way of telling someone that you're like a 10x dev, you know? It's like you don't use the word 10x anymore, you're cracked. And what's crazy is, and I couldn't believe this, I was there's a guy that left OpenAI and started his own company. I can't remember his name because again I'm crap with names. But he just got like a $1 billion investment. And I went to their website and he's like, hey, we're hiring. We've just had a $1 billion investment into our new safety AI company. And I read the job app, like the job introduction, and it was like, we're building a cracked dev team. And I'm like, oh my God, it's on job applications already. Oh boy. Exactly. It is, you will be on crack because we need you to work 24/7 to show our investors that we're a serious company. Yeah, and that was, they're using that word That was a West Coast US company that are using that word. And I've seen it. If you search for like on tech Twitter for the word cracked, you'll just see more and more people using that word now. So yeah, add it to your vocab, guys. You are obviously crack devs, being in a stream of someone writing an OS. You know, you're crack devs. Welcome aboard, my fellow crackers. Oh, I should not say that, should I? Holy crap! Scratch that. Yeah, Walker, when I found that site, I wrote a tweet about using the words crack dev, and I felt so cringe writing that tweet. I deleted it like 2 minutes later. So I can't, no, I'm encouraging this term. Like, I just can't, man. And I'm like, delete. I hope no one saw this. The tweet was sacrificed to the cringe lords. Yes. Exactly, Victoria. If I may, how many revolutions around the sun do you have? I am 39 years old. I am 40 next May. You are what we would find in a pyramid. Brilliant. I love like silly comparisons like that. I heard one recently and I love it. It was something like, you're as useful as a fart in a tornado. I thought that was hilarious because I've never heard it before. I'm like, oh, the comparison is beautiful. And a fart's useful. I have no idea. So back to the SDM. I have to say, Marion, if you're used to, I think you've probably read this before or had some dealings with it, and I have low trust in this document. And I'll give you an example why. Because I was in Discord and I was questioning my sanity about the wording that they used in one of the page table descriptions. And some dude was like, oh yeah, it's actually this location because it says this in the AMD documents and it describes it better. And I read the AMD one and I was like, yeah, that's exactly what I thought it should be saying. So it's like the document is painful. It's not perfect in how it words shit. It's like confusing sometimes. And it is painful. Yeah, it is actually painful. And many times I question my own intelligence. Like I'm reading a paragraph and I'm like, why did I not understand this? Like, am I cut out to be an OS dev if I can't read this manual? And then I ask people and they're like, no, dude, the document is shit, really. Let's get back to where we were. We were like, these VODs go up to YouTube, by the way. So I only say that because there's a lot of people on YouTube that love watching hobbyist OS developers because it's like sleep pills for them. Like, they love seeing somebody read through a crazy document, talking to themselves, talking about nonsense shit that no one can understand, and it's like white noise for them, and it sends them to sleep. So every time I put these VODs on YouTube, they get like 500 views at the moment because I've not been uploading them for long. But a lot of people, like initially, are watching these videos and use it. And I've had comments saying like, "Oh, thank God, a new guy to listen to." Like, I've been getting fed up of this other popular guy that does OS dev streams, and I finally got some new content to fall asleep to. And it doesn't help too that a lot of people will say like, "Oh, you have an ASMR, you've got a soft-spoken voice, and you put me to sleep." I'm like, "Thanks, man. I want to sound like engaging and, you know, and you just, sure, go ahead, fine, do it. Take it from me. I don't care." All right, let's go back to where we were. Here we are, paging. Right, so the code. Yeah, to be honest, I think one of the craziest things that happened when I started on this journey was, well, there was 2 points that I felt really good about myself. I was reading somebody else's OS code, and I pointed out that they had a bug in their code because of what I was reading at the time in the documents, like in the development manuals. And I'm like, "Hey, I've got a feeling you've got a bug in your kernel here because it says this in the software development manual, and I've got a feeling you've missed something here." And I posted it to them in a DM, and they were like, "Holy shit, yeah, thank you. That was actually a bug." I'm like, "Holy fuck, did I just fix someone's kernel?" Like, bug fix someone's kernel just by looking at the code. In like my first 3 months of OS coding, like, it was crazy. I'm like, "Holy shit, I spotted something." And then somebody else who's so that guy who's writing his operating system in assembly, a lot of the open source operating systems choose not to use a certain chip on the motherboard called the HPET timer. So the HPET timer, you may have heard of it in games. In the OS, it's called like the high performance something timer. And a lot of people are like, "Oh, you don't need to do that timer. You can just get away with using like the standard motherboard." Like, there's another timer. There's a bunch of timers that you can use, and you can pick to which one you want to use. And some people will go like, "You can just use this other one, and it'll be enough for what you want to do." But I was like, "But I want to learn how I get the high performance one." So I wrote the driver for the high performance one, which is all of this shit here. And this was really painful. This took me like 2 weeks, and it was buggy as fuck. And I checked Linux, and the developer in Linux had wrote tons of comments saying how buggy the HPET timer is on motherboards. So it's painful just at the hardware level. But I got it working. And the assembly OS guy was like, "Oh, hey, thanks for writing that code in your OS. I've used that to also implement the HPET timer in his assembly version." And I'm like, "Holy fuck, now there's like people learning from my OS." Checking how accurate one timer can be. Yeah, it's crazy how fast this timer fires. I may have wrote it down in a comment somewhere. Like, the high performance one is like millions of times per second. God, this was like 6 months ago, and I should have commented it. Like, I need to start putting documents in code. Because the code itself is way too abstract. But yeah, the community, the OS dev community, is super nice because everyone knows it's painful and they love helping people get to resolutions. But one thing's for sure is you have to prove to people that you have RTFM'd, you know? Because what happens in the OS dev community is you get a lot of first year university kids and they find the Discord and they're like, I've got homework to write a memory manager. Please tell me how to do it. And it's so repetitive, like every year, this wave of students that find the OS Dev Discord and they just ask the same noobish questions that are all in the documents, and it pisses people off. So you've got to at least prove that you've attempted to read and reference like other operating systems. So like I've got another one. There's like so many references that you need to have when writing an OS. It's crazy. So yeah, I've got like Minix, Plan 9, Redux OS. There's another one called X86, I think. Let me see if I can find it. Yeah, here it is. So you just need to find other OSs that are just way more mature than what you're doing. And you'd like go in here and you're like, okay, cool, someone's wrote their own OS. You find like everybody names the same files very similarly. So like you'll find the virtual memory manager in vm.c. So I can pop open this person's vm.c and I can be like, right, okay, how did you do your paging, person? And I can look at the structs that they made, how they're walking the page map, you know, the kind of like bit masks they're using, and you're like, okay, am I getting what I'm doing? Is this like similar? Am I on the right path? And there's no fun in copying someone's implementation. I find that completely boring and misses the fun for me. So like this, when I look at this VM, for example, they've got calls here to my CPU. So what that tells me is they've already got the maturity of having like multi-core and program level memory spaces. So it's even a bit more mature than what I'm aware of, like what I can digest. Oh, they run OS Dev on IRC. That's cool. 2 years ago, I was trying to read about how to sync two clocks using quantum events, and that's how you got the HPT. Oh, that's cool. Yeah, I think the other timer is called the Pit. I wonder if this guy's got it. So it'll be in CP. Usually there'll be like a pit.c or something. But yeah, the other timer is the Pit timer, which all I do is turn it off. Like, I just write these values to a port address and disable it. Twitch chat is IRC. Where's my manual? But yeah, Temple OS, yeah, it's another good reference, even though that project is probably too mature. Like, it's been going on for so long, I'd get lost in the source, so to speak. it's certainly nice at the moment just reading the SDMs. I think I've lost my tab. Let me just grab the right doc. Here it is. I found it. Yeah, so we made ourselves, we were reading down the paging stuff, and we've made a little shopping list of work we need to get done. So we've got to know when we've got 1 GB page support enabled. And we need to early exit the walk if we've got one. And then I think there's another one, like a 4 meg one, I think, or 2 meg. A lot missing from Terry's OS. Oh, really? I thought it's been going on for so long and had like a very large community around it. Yeah, we need to finish reading down this here. Only kind of got halfway down. So in the thick of the VM here, I was kind of doing this bit masking on the entry addresses, and I know it's wrong. I did it last night, and I'm like, I need to go and fix that today. So we've kind of fixed it using this mask that we've read from the SDM to say that it's in like bits 12 to 51. So we're using that mask now to grab the correct memory address from the entry. Yeah, I think that's another thing too of like, I've got a goal, right? Because an operating system is an endless project. And my goal was to get to a point where I wrote a tweet, right? I posted a tweet to Twitter or something that's like "Hello World" from BlorOS, right? But I've like tagged in a few things along the way, like I want file I/O and I want graphics and or some 2D graphics. I definitely want file I/O. I definitely want a 2D graphic like Windows environment with like I want to have the concept of writing a scheduler. So I want multiple processes on multiple cores. And then I want to have it so that I've got a HTTP driver, HTTPS driver, and then I'm handshaking SSL, all that kind of stuff. Yeah, so sockets, TCP, HTTP, HTTPS, which, I've got to get into ciphers and SSL handshakes and all that kind of stuff. And eventually get to Twitter and be like, I made it. I am BlorOS. I'm here. Hello, world. I am born. Oh, I shouldn't have mentioned the word Twitch on Twitter because now I'm getting like DMs for, do you want some graphics for your channel? I've heard sockets isn't too bad, Marion. TCP, I'd beg to differ. HTTP, probably not bad, but definitely HTTPS is probably a pain in the ass. And the SSL handshake is probably a very interesting thing because you need, at that point, you need a library with all the cipher encryption and decryption stuff in it to complete the handshake. And you need those algorithms to obviously decrypt all the traffic and encrypt the traffic going out. So that's a bit of a mountain. Fun one though. Like I'm not alien to what the SSL handshake is. I've many a time had to Wireshark into SSL connections to find that two servers couldn't agree on a cipher to use and therefore refused to connect. Yeah, PCAP, Wireshark stuff. The thing about the cipher is you don't need to be a genius to do it right. The cipher is, it's an algorithm that has been created, and it's been created by a genius at some university who has then published the code in many forms, in many languages, and I would absolutely not feel bad about copying and pasting that cipher. I'd be like, yeah, this is not my cipher. This is made by blah blah guy. I'll give him all the credit. The code came from here. Like, I am not a genius and I'm taking this code from the public domain, you know? Thank you very much. It's like if you were to do, I don't know, MP4 or FFmpeg stuff, you know, again, it's all so algorithmic based, and I'm not here to prove that I can write an algorithm that can do video compression. So I would like those features in my OS, and I will just plug them in. The thing that I'm finding satisfying is doing like the device and the OS kernel, like the scheduling and the memory management and the core management. I can't wait to get into turning the cores on and giving them some memory, like a stack, and having a program with its own stack and its own memory map. That would be fantastic. And I think it's exciting knowing now that summer's over and I'm going to spend my time now again on this OS deep through autumn and winter. So I'm getting a feel for how, like, there's some commonality in writing OS code. Like when you're writing a driver, you know, okay, I'm dealing with a bunch of registers, I'm dealing with some memory mapped IO again, and you're repeating what you've learned before. But yeah, like even the driver setup, right? So getting to a point where you can actually store a device driver external to your kernel. And when your kernel boots up, it brings the drivers in on load, right? And having, I don't know, a shared lib. So like what Windows does is the API to making system calls is stored in kernel 32.dll. It's stored in msvcrt.dll. And it's loaded those drivers into a permanent area in RAM. When it loads an exe, it maps the function addresses into that exe. And then that exe uses those shared memory locations to run those kernel system calls. And I'm like, okay, well, that's a cool idea. I'd like to try something like that, you know? Like having a custom header over your program binary. And, you know, like the Windows header over a binary is the imports and the exports functions that it maps through other DLLs in the system. And obviously Linux works in a different way, but again, you can like, it's exciting to know I can take those ideas and I can be like, oh, that's cool. I'm going to create my own XE format, you know, in the flavor that I like and what I want to do. A good if you ever want to like, if you're ever interested in seeing how Windows runs a program, there's that NSA tool called Gaia. Can't remember what it's called now. I think I've got it installed. Somewhere. But you can pop open an exe and it will decompile it all. It will show you all of the drivers that it's connected to. It will show you Gydra, yeah. It'll and you can find the main function and you can look at the tree of what it's doing, like what Windows is doing to boot that exe file. And kind of like turn an exe inside out and really understand how Windows is working with that binary. To be honest, I know more about the Windows binary sequence than I do about the Linux one. I wonder how Linux works. I'm willing to bet it doesn't have as much elaborate ceremony as Windows. Yeah, IDA is the other industry standard, right? IDA Pro. Yeah, IDA Pro, de facto standard for the analysis of hostile code for InfoSec stuff. But they're really good. I mean, I've got into those tools because OS dev is all about getting into the insides of things, right? So you want examples. You want to see how is Windows doing this thing? How is Linux doing this thing? And those tools are really nice to just crack the egg open and be like, okay, so that's how it's doing it. And when I read about the Windows process of auto wiring the kernel call addresses into the program on startup before the main function is invoked, I was like, well, that completely makes sense, right? Because you don't want to duplicate that standard library in every exe that you have. So it makes sense that there's this auto wiring process on boot up. Controlled. They're really good learning tools, I think, like malware. I think everybody in the like first couple of years of dev probably got wrapped up in some kind of malware thinking, or it's quite a common thing actually. Like, oh my god, I've got this power. You know, I control my friends by writing a virus. You know. I mean, I certainly did. But yeah, that the guy that solved that WannaCry bug, that was such a crazy event. Like he was working for a company as like an infosec guy, and yeah, Marcus, and he's like, oh, I disassembled WannaCry and I found this endpoint that turns off the virus, and he sinkholed, the communications of WannaCry. And then the FBI arrest him. It could have been the CIA. I'm not sure. But they were like, oh, this is the guy that when he was like in his teenage years, he was selling malware. Let's arrest him. So he got famous. They were like, oh, let's arrest him. And then they arrested him. And I don't know what came out of that. That lasted for ages. He's free now, so obviously nothing bad. But yeah, he was like his young career, his early days, was just all malware shit. Yes, Marcus Hutchins. I don't think he's on Twitter anymore. He's on other social media. I think he left Twitter. But he was at he does still visit cons and stuff. People still see him. I see the occasional picture of him. Oh, he's on Mastodon. Damn, I haven't heard of that for a while. Man, this has been a great catch-up stream. It's kind of good though, like the first stream back, I kind of need to like set my plans for the months ahead, kind of get a gut feel to what I'm going to be doing over the next few weeks. So like this virtual memory module, if you like, I'm probably going to be in here for a couple of weeks. I want to get to understanding paging very well. Like I want to be able to say to people, I know it inside out, for a 64-bit environment. So I want to respect things like these 1 GB region processes and these this 2 meg region. So at the moment, all my VM assumes is I've got a 4K page. So I need to add support for 1 gig and 2 meg. Yeah, so many confusing lines in here. Because a PDE is identified using bits 4721 of the linear address, it controls access to a 2 meg region. Is that more about I've got a feeling that I'm not thinking about that line correctly. And I'll be honest, I am a bit confused of when it uses terminology like a 2 meg page. Because a page to me, all I know a page to be is a 4K boundary in the PM, which is the physical memory manager. So that is a page to me. Like it's a 4K block of physical memory. My physical memory manager does not deal in anything other than that. So what I'm almost thinking that I'm not understanding is, do they assume that this is a region that if you stop at this point in the map and you've not bothered to walk down in more detail, your entry is just identifying that, okay, you've got all the regions underneath you and the total for them are 2 meg. So it's like, okay, you've got this entire region. We don't need to go any further. It's just all yours, which makes kind of sense. the more I talk about that. So like if you stop at the first level, you're in control of, like it says here, it controls access to a 1 GB region of the address space. And it's just kind of like it's an early exit from the paging walk, because you're like, why do I need to go into detail to find where you're mapped to when I can just stop here, tell you that you're in this 1 GB region, and here's the offset in that region. And I think that's what it's doing. Oh, good. It's got diagrams for these different states as well. So like here, you've got like, so you've got a memory, a virtual address, and in that virtual address, you've got a 20, so you've got a 30-bit offset. Whereas in the smaller 2-page one, you've only got 21 bits. And in the normal 4-byte, like when you've walked the entire table, so you've gone down all 4 levels, you've only got 12 bits for the offset. Because you're in a... The reason you've got... Sorry, I'm thinking out loud here. The reason you've got the smaller offset at this page level, because you only identified a 4K page. You don't need a lot of room to declare an offset, because it's just 4K. In a 2 meg space, I need more bits to declare my offset. In a 1 gig space, I need more bits to declare my offset, right? This makes logical sense now. I get it, kind of. Yeah, I think that's exactly how this is working. So like when these flags are saying, you can stop here, you're in a 1 gig page, I can be like, okay, 29 bits or 30 bits in my linear address is my offset into the 1 GB page. And we can resolve that page address. And again, it tells us how to resolve that address with the offset, and bam, we're at our physical location. I'm comfortable with that theory. It makes sense in the pictures. It makes sense in the way it's describing it to me. I think we've leveled up there. And I'm going to take that as a win, right? Understanding something from this manual is a win. Like, okay, I'm not going to code anything yet, but we've understood something. It's even better. And like, you know, it took me some days to actually crack out that code in its current form. So understanding the process, like it was a paradigm shift to understanding that the virtual address was a set of keys. So a single 64-bit value is a set of keys, 4 keys into 4 different tables. And that kind of like the penny dropped, you know? So like, this is my variable. This is like, here's a pointer with a variable, and here's its location in memory. It's not, it's kind of its location in memory, yes, but it's actually a set of keys. It's a set of pointers into different tables. And I love repeating that theory to myself, because I'm like, I'm reliving the dopamine of when that happened. And I'm like, yes, I understand now. And when the OS devs in Discord, they were like, yeah, it's just a radix tree. I'm like, I don't know what a radix tree is. I've never written one in my life, right? And then when you Google it, you're like, oh, radix, yeah, that's an IP address, you know? Everyone's used them in IP addresses. That's what they are. So like, you know, octet, 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 you've got 4 keys there. That's a radix tree. And that's exactly what a memory location is here. But we've got an extra value, which is the offset. So it's like, here's your selection into your warehouse of where your physical RAM is. And the actual location in this, the actual place in memory is right here in this offset. In after you've walked that tree of pages. And I think the other like mind-blowing thing is understanding how big the paging directory is. Like the first page, and then you've got 512 indexes that you can reference. But if you're going to the next index in that table, you've got a different set of 512 indexes that you can reference. And the next guy, index 2, has a different set of 512 things they can reference. And you do that 512 times. Thanks for dropping in, Walker. Yeah, thanks, buddy. See you again soon, mate. Are we talking L1 cache? I think so. When you say L1 cache on us, they're probably modules. Yeah, they're modules inside the CPU that are saving time. So they're like probably watching how often you're accessing certain locations and deciding to shortcut cached values. Because I notice in a lot of these page entries, you can set cacheable or non-cacheable. And that's probably assisting the L1, L2, L3, and L4 caches on the CPU. Which is the same concept of like garbage collection almost, right? Like the generations that you sweep and promote less used variable access to and from. I think it's kind of the same concept. I may be wrong. But I can completely understand how those L1 to L4 cache modules that live probably very close in the CPU to this memory resolving, memory lookup concept of paging. And they're moving through those caches and save you taking a trip down to the RAM chip. Like we don't have to leave the CPU, we've got a cached version and we know it hasn't changed. And we know you just access this, so cache hit, you know? But I've just not read how that works inside the chip specifically. I'm just guessing at this point, but it feels likely that that's how it's operating. Yeah, so someone mentioned on Discord that after I've got over this virtual memory manager, you should be able to just plug in 5-level paging because all it is an extra table to walk down. I've been taught through some reading is that the L1 cache should have a write-through set to avoid interacting with it while ensuring cache coherency. I'll be honest, I've got it on the back burner of my brain to go and learn what it means to be write-through. I see this on a lot of documentation, like even in like the MMIO stuff, like in manufacturer device documentation, they talk about write-through, and I've got a feeling it's in these SDMs somewhere of what that actually means. And now that I think about it, does it just mean that you you jump the cache, and that the whole word right through just means that screw what's in the cache, I want direct access, like let's just go. Oh yeah, because it's ringing a bell now. Like I've seen documentation talking about refreshing the caches and stuff if you've done writes. That could be at the page tables though, changing the page tables. All right, stopping my brain there before it runs off down another rabbit hole. Um, do, 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 do. I love how somebody in that post just says like use Fortran. There's a reason Fortran still exists. Okay, I'm getting pretty confident now that we've had a good chat about those different early exit regions. I just want to kind of confirm that this is something that's kind of something you have to check for. So that's file level paging. This is a 4K. Like here, for example, like there's no early exit on the first table, but it's like if you did, you'd be declaring that you control 512 gigabytes of memory. So this is lining up to, okay, if you stop at the first level of the tree, you've actually declared that you own all of these regions. You greedy page of memory, you. AB trees in Fortran 70 tabs. Man, I don't think I've ever seen Fortran, or have I? I think Walker may have been doing some Fortran on Twitter. Well, this is wild. It says like HLAT paging. If bit 11 of the PML4E is 1, translation is restarted with ordinary paging with a maximum page size of 512 gig. I'm trying to understand what it means with this statement here. Bits 3 to 11 are bits 39 to 47 of the linear address. Anyway, I'm pretty happy that we've got this correct now. Physical address is specified in bits 12 to 51 of the PML4E. So that's this operation here. Sorry. I've actually fixed it in a level too low. No, that's right, actually. Physical to virtual, PML4. That's the PML4 entry. And then we're bit shifting the PML4 entry across 12 bits and masking it for 40 to get the physical address. Yes. A PDPTE is selected using the physical address defined as follows: bits 51 to 12 off from the PML4E. Did I write those in code as this? So we've got the PDPT, we're using the index to look it up, and then we've got the entry. And it's saying here that use of the entry depends on its PS flag, which is bit 7. Which is caveated here. The PS flag of a PDPT entry is reserved and must be 0. P flag is 1 if 1 GB pages are not supported. Bit confusing there because it suddenly says if the P flag is 1 and talks about the PS flag. I'm wondering if that's in the diagram. Yeah, it's a bit confusing, that one. Talks about the protection key too. I wonder. Let me check. This link. Did I see I32 doc? No. What is this? Oh, it's a machine readable format of the documentation. I wonder if that's just for like feeding into an AI or something. Like AI training, maybe. Um, Let's go check the VM here and look at the walk here. So this is someone's walk routine in a different OS. So I'm not sure why they're doing this. Like there's literally a mem set here. Oh, because it supports allocating pages. I've got to be careful there. So you can send a flag in here as one and it will create page entries. If not equal to alloc, or wait. Oh, if present. If not present, it checks if it can allocate. I get it. So it looks for the first unallocated entry and then starts to perform allocation. That's something else we've got to attack later on. So I mentioned about walking virtual addresses is one facet of this problem. And the next facet would be, okay, well, how do we create entries? And fortunately, looking at this code, it doesn't look too bad. Like they're doing a physical allocation to grab a page, and then they're mapping it through by setting this non-present page to present, but also making it writable and user mode. I understand why they've got this comment here now about the permissions are quite generous, because they're probably just going, your page by default is user writable and present, and they're your default page permissions for all kinds of pages. Okay, so if we don't assume that and they're walking down the page, why does this instantly return? Is it? Oh, yeah, it's called repeatedly. That's why. This is the recursive. Map pages, creates page table entries for virtual addresses. Load UVM, loads a program into a page directory. Deallocate, clear, copy, map user virtual address to a kernel address. See, I'm getting confused by reading this. It's a bit dangerous when I start stepping into other OSs sometimes, because I'm like, the way someone's implemented it here is probably in a different state of mind than where I'm at. So it's kind of a bit harmful sometimes looking into this. I was hoping for a certain hint of something and I didn't find it. I'm left more confused. So I'm going to go running back to my SDM. Did I close it again? I'm so bad at keeping this manual open. Zoom in a bit here. We're I kind of need to like print these pictures out somewhere other than the document. I need them like on a monitor permanently so I can keep referencing them so the information gets burned in my brain. Thanks for following H. Paul. All right, I'm going to ignore the HLAT paging because that's to do with, I believe, VM stuff. Oh my goodness, look at that. So if you have 5-level paging, each index in the first table gives you 256 terabytes of address space. Like, why would you need that? I'm wondering if that's used in like server-side server CPUs that have literal terabytes of, yeah, supercomputer regions. Yeah, you'd probably want 5 levels of paging to access terabytes of RAM. So we start here. So again, I keep having to reread to make sure that I'm implementing what I need to and what I don't need to. What I honestly can say, 1230 to 51. I think I do need to implement this. But the thing is, if I'm not creating 1 GB pages in my map or 2 meg pages, then they don't exist. So we could get away with just having 4K page support and, be done with it. I say we get comfortable with just having the 4K page layout set up, and then we can progress to adding the 1 gig 2 meg page support later on as features in the VM. If I can just get my 4K walking correct, that's the good focus for now. So I'm kind of like thinking that we need to do this all the way down. Is it the same in every entry? I think it is. Like an entry has the same shape as any other entry. Bits 12 are from the PML4E, bits 12 from the CR3. Oh, okay, I'm at this bit here. A 4K naturally aligned page directory is located at the physical address specified in 1251, so it's the same. 12 to 51 to get you to the next PD entry. And again, that's the PDPS flag 1, which we're not doing. That's the 2 meg page case. And this is the non 2 meg page case. So we're back to a 4K byte, 4K page. And then it's the same concept, bits 12 to 51 again. So it is. And again, 12 to 51. So I'm kind of... And then we need to do the offset, which is this bit here. So let's go fix, back to the code now. Pretty sure that these entries are all having this same extraction of using that 40-bit mask. So the PD, again, bit shift 12, and the address mask. Job done. And then it's about applying the offset. So we've got the macro for grabbing the offset from the linear address, which I'll also verify. And then this application here needs definitely verifying. This is probably wrong. I'm just going to put here what were they? No support for 1 GB or 2 MB pages currently. Just so people understand that if they're using my OS as a point of reference, one of the really cool things about doing my own OS when I'm looking at other people's OSs is I'm like, oh man, when I go and look at other people's OSs, I wish they'd comment the shit out of what I'm looking at. And that's one thing I like doing with my own, is just commenting the crap out of what I'm doing so that when other students of OS dev pop my OS open, they get all these juicy comments about why the things are the way they are. Like, I even made reference here to the Intel SDM. All right, so we're pretty close. I'd be happy if we can get this done tonight. I know it's midnight almost here, but it's Friday tomorrow. So the PTE is the bottom one, right? Yeah, the page table entry is the bottom one. Every PT maps to a 4K page byte. C table 420. Okay, bit PT is 1. Translation is restarted. Okay, we don't care about this. Otherwise, the final physical address is computed as follows. Here we go. Bits 51 to 12. Again, our standard bit masking. And what we're going to do once we finish this, by the way, is because the masking is repetitive and the structure of the entries are identical, we can collapse this entire code block into just a for loop. It's like, let's do 3 iterations. Then if we want to do 5 level paging, we just up that by 1. And bam, we support 5 level paging because we're just doing an extra iteration on jumping down the tables. Bits 51 to 12. Okay. Linear addresses, protection key. No, hold on. Otherwise, final address is computed as follows. Okay, right. It is 51 to 12. Check. We're doing that. 51 to 12. Here. Wait, PTE. Oh, hold on a second. We're shifting here. And this is being ANDed against the bit mask. So that's our fix to addressing the 12 to 51. Okay. And then here we're ORing the page offset from the linear address. So it's saying bits 11 to 0 are from the original linear address, and yes, 11 bits being extracted there from the virtual address. So that's 11-bit hexadecimal. And then the linear address protection key is the value of bit 62 to 59 of the PTE. Linear address protection key, the value. Protection key, question marks, question marks. If a page instructor entries P flag. Oh, I understand now what it means by P. That's the presence flag. That's just the first bit on the entry. Is it present or not? AKA enabled. So if the present flag is 0, or if the entry sets any reserved bits, the entry is used neither to reference another page instruction nor to map a page. There is no translation for a linear address whose translation would use such a page instructor entry. A feature to such a linear address causes a page fault. That makes sense. You've reached the end of your traversal, and your last traversal entry tells you that you're not present, therefore you don't have a mapping. And rightly so, you should have a page fault exception. But that's the behavior of the CPU, because what we're doing here is we're walking down these page tables, but that's also what the CPU itself will do when we use instructions on the CPU later on. So it'll do the same of looking at the CL3, walking the page tables, and getting to a resolution itself. The following bits in a page instruction entry are reserved. So what I'm not getting from this is, why have I ORed the offset onto this address value? Why would like mentally, I'm like, why are we just not adding? So this code initially was taken from somewhere else, and I'm like, why are you ORing this? There's nothing in this document telling me how to use that offset. CTable 420. Table 414, format of the PML5 entry that references a PML4 table. Oh, this is what I needed earlier. So, P here, for example, is telling me that the P is the present flag and it's in bit 0. PS is bit 7. Format of a PML4 entry. So again, so this kind of verifies that the checks here on the entries. So they're checking bit 1, which lines up to the documentation here, right? Overwatch is updating while I'm streaming. No! So it's a structure breakdown. Okay. So that's the read-write status, and that's user supervisor status. So these are this is the permission structure that we have across every single allocated chunk of memory. We can say if it's read or write or not. So we can declare, I don't know, maybe some kernel config that we never want anything to touch. We can tell the CPU, you're like, yo, don't ever write in this location, and it will respect that for us. So we can set like virtual pages in the kernel to read only. And then this user supervisor. So if 0, user mode accesses are not allowed on the region controlled by this entry. That's cool. So that's separating our user programs from our kernel. And it's like the CPU is protecting user programs from reading kernel space. Is it though? Like, to me, the kernel just has its own virtual memory map. Like, it's just entirely different to anybody else's. So why would you want mixed user supervisors in that tree? It's a bit confusing. Page level write through. So bit 3, PWT, indirectly determines the memory type used to access the page directory points table referenced by this entry. And I need to read on to section 4.92 to understand that, and we need to. Page level cache disable, indirectly determines memory type. Accessed indicates whether this entry has been used for linear address translation. Interesting. It's these pages are the same. So that's a 2 meg page. So the structure is all documented here, that if we did want to do the 1 gig 2 meg support, it's all here. But I think, yeah, I think we're just going to stick to doing the 4K one at the moment. I'm just a bit bummed that I don't understand how the offset is being applied. And protection keys. So we need to read that some other day. Translation, look aside buffers. Page numbers, frames, and offsets. This is a lot to read through. This is going to have to be for another night. I think we've made great progress on fixing the code down to this point here. I just need to double check. I've accidentally got rid of another line of code there. Oh no, I moved it. Lol. But yeah, just tagging on the page offset. I just need to double check that in somewhere else, and then we can kind of start trying to fix testing this. And I think the allocation step we can also open the door on, because that's quite simple. You're saying walk the page table until I find something not present, and then when I found something not present, go ahead and make it present. So we switch it on, we fill it out with some numbers of what we want to start allocating. We end up at a physical page. We get some memory from the physical memory manager. We pop the physical address in, job done. So that is kind of close now. So we're almost now at the point of where I can say, okay, yeah, we get the memory manager offset added, and then we open it to allocating page. And now we can support the function of mapping. So I can expose a public function that says like map me some physical memory. And you're going to be like, okay, how much memory do you want? 2 meg. And it goes away, grabs 2 meg worth of physical memory, maps it in the memory manager, returns you back a virtual address. So actually the other step we have to do is building the radix key, if you like, or building the virtual address from the creation of a new entry is a chunky step. Quite simple, because I'm just piecing together the offset and the entry keys into the variable, the 64-bit variable. So once we've done that, actually that's a good thing to test, like end to end. We've got walking, reading, we've got creating the page table entries, and then we'll have creation of the virtual addresses, and then we can feed it back through and say, okay, let's walk that virtual address I just created. Am I going back to the physical address that I just registered? And that completes the unit test of quite a lot of the process. So we can kind of keep forging on in theory, and then just see it all testing with creation and walking later on. And I do need to collapse this function now that I've seen the abstraction in it. So yeah, it's this chunk of code here, like the lookup, the entry, the verification of the entry. It's all the same. Okay. Yeah, I'm gonna close the stream for the night now, I guess. It's midnight. We did a good 3 hours on a work day. That's pretty good. But yeah, I'll be back tomorrow night for a longer stream and the weekend. So I'll be here for months and weeks ahead. So you'll get to see the OS growing yet again, season 2 of BloyOS. And thanks for popping in again. I'm glad to see some faces from 6 months ago. That was what I was hoping more than anything. Some OGs. But yeah, thanks for watching, buddy, and I'll see you tomorrow if you're around. Have a good night.